In this video, we're going to focus on interpreting the derivatives that we've now found, the higher order derivatives. We're going to start with a function, z equals x squared minus y squared, and we're going to find both the first and the second partial derivatives evaluated at a single point. So we'll start with the first order, and that would be the partial derivatives with respect to x and with respect to y. I'll write them in this subscript notation here. And the x partial derivative is simply 2x, and the y partial derivative is simply negative 2 times y. So we have those two first order values, and we can calculate those at the point negative 2, 1. We're going to get fx is equal to 2 times negative 2, that's negative 4, and the y partial derivative will be negative 2. Not too bad so far. We can then go to the second order partial derivatives, and what we'll do is the matched ones first. So we get this xx partial derivative by taking another x derivative of this. So we start with this function, we take the x derivative, we're simply going to get the number 2 when we're done that. If we want to find the second derivative with respect to y, we would get that by differentiating this expression here, the y derivative once, with another y derivative, and that's going to give us, if we take a y derivative of this, negative 2. And last but not least, fxy, well, that we can take any way we like, we've discovered. So what we'll do is the x derivative now, but start with what the y derivative was, and that the y derivative was negative 2y. And if we take an x derivative of this expression, there are no x's in it at all, so our partial derivative is 0. So here we have 2, negative 2, and 0, and it's actually true at any point, but let's add this in a nice column here for the purposes of our notes. At the point we're interested in, here are the first order partials, and here are the 3 second order partials for this function. Now we can take a graphical look at this, noting that our x partial derivative, going back, was negative 4, y partial derivative was negative 2. How is that reflected on our graph here? Well, remember that this point is the point negative 2, 1. And what we're talking about with the x partial derivative is a step in the positive x direction. We increase the x value. Let's actually keep our color scheme consistent here. We have fx equals negative 2. We have fx equals negative 4. And that means when we take a step in this direction, we're going downhill. Well, we can see that perfectly on this diagram. We're going downhill, and it actually seems to be fairly steep. We can contrast that with a step in the y positive direction, where y is increasing, and we can see there we have a slope that's downhill again, but a little less steep, a slope of negative 2. And we can capture that here in words as well. So from this one point, if we choose either of these directions to travel in, we're going to be going downhill, but it's going to be a little bit steeper if we go in the positive x direction on the map rather than positive y direction. Now, what about the second derivatives? Well, we found earlier that the second derivative of this function, which we could write in either of these two notations, was positive 2, while the second derivative with respect to y was equal to negative 2. So let's imagine the same kind of scenario. We're still at the point negative 2, 1 on our map. We're still taking a step in positive x or a step in positive y. And what we see when we increase x is a shape. Well, what shape is that? I can imagine tracing this out. And remember what second derivatives were for single variables. Well, all we're dealing with is a single variable here. What we see is concave up. Well, for concave up, notice we have a positive second derivative. But only in that direction. If we take steps in the y direction, make this a little more parallel here. If we take steps in the positive y direction, y increases. What shape do we see there? We see concave down. And that matches perfectly with what we see as a value here, that the y partial derivative is a negative second derivative. So our intuitions that we built with single variables, which were that positive second derivatives mean concave up, still applies. Our intuition that negative second derivatives imply concave down still applies. The only new part is that it's direction-based. We can have concave up shapes in one direction and then concave down shapes in another. That's entirely reasonable when we're talking about surfaces. Now, of course, this leaves one question hanging, which is, what about that mixed partial derivative? What does that represent? Because there's no analogy for that when we only had one variable. That's what we're going to explore next.